Good morning, everyone. In the last class, we had done with a few properties related to Z transforms. Let us continue in today's class also. The next property that we are going to discuss is time domain. Convolution in time domain. As we discussed in the module number 2, we had x of n and I give it to a LTI system, that is linear time invariant system, and the output is y of n. Okay, so now if I want to take the Z transform of the input signal and this one, which is nothing but an impulse response, say h of n, I'm sorry, I should write it as h of n here. So this one is y of n as the output. So how do I obtain the Z transform of it? Okay, so starting with the first one, which is the convolution being applied, x of n convoluted with a signal, say y of n. Okay, so this is a general representation. What I've written here, it is a general representation. So now, as I move on to two signals, say x of n convoluted with y of n. So what I can do here is I can have sigma, how I can express it in terms of the convolution domain, that is time domain, k is equal to minus infinity to plus infinity, that is x of k, y of n minus k, x of k multiplied with y of n minus k. So now if I take the Z transform of the individual signal, say z of x of n, that would be equal to x of z, and Z transform of signal y of n, that would be equal to y of z. Okay, so now I have taken the Z transform of two individual signals. Similarly, the Z transform of convolution of two signals, would be x of z into the normal multiplication x of z multiplied with y of z. So now if I want to take a complete signal, this is the convoluted signal which is there. So this convoluted signal, I can write it in terms of the summation, that is for a Z transform. So sigma n equals minus infinity to plus infinity x of n convoluted with y of n multiplied with z power minus n. Okay, so now this convoluted signal x of n convoluted with y of n, so what I can represent here is I can write it as sigma n equals minus infinity to plus infinity, sigma k equals minus infinity to plus infinity. This convoluted signal would be x of k, y of n minus k, that would be multiplied with z power minus n. Okay, so now what I can do here is I can make a substitution for n minus k. Substitute n minus k equals m. I can call another variable, say m. So I need to substitute n minus k equals m and interchange the order of summation. Interchange the order of summation. Interchange the order of summation. So now I have interchanged the order of summation now. So what I can do here is I will be taking out n is equal to minus infinity to plus infinity, and I can write sigma k equals minus infinity to plus infinity I can write, and I have x of k times y of n minus k, that would be multiplied with z power minus n. Okay, so what I can do here is I can interchange the summations now. So if I take the Z transform of x of n convoluted with y of n, I can write sigma k equals minus infinity to plus infinity, say that is x of k z power minus k. So that is again multiplied with m equals minus infinity to plus infinity. I can have y of m z power minus m. So what you can conclude from this step is, so each and every individual will have the Z transform expression which is in a mathematical way. So it is expressed in a mathematical way. So this is for signal y of n. I can write it as this one. So here, if I take the z transform of y of n, I can write it in this manner. This is y of m. So this one here is x of k. So that is x of z multiplied with y of z. So that is the z transform of x of n convoluted with y of n. So that's how I can write it. Okay, so z transform of two convoluted signals, say x of n and y of n. So how I can write it? I can write it as x of z multiplied with y of z. Okay, so that's how you can define the function, that is the convolution of two signals where the z transform is taken into picture there, right? So now the next property goes this way, which is the time reversal. The next property, that is time reversal. Okay, so in time reversal I can write it like this. So if I take z transform of a signal, say x of n, that would be equal to x of z. So time reversal, I can reverse the time, that is minus n. Okay, so you have ROC, so z belongs to ROC, say Rx or something like that. That is the ROC which is present for the first signal, say x of n. So next I have x of minus n. So that would be x of 1 divided by z. So you need to take the inverse of the z term which is there in the algebraic expression, right? So now this z would be belonging to 1 divided by Rx. So the region of convergence, is z, which is the reciprocal of the ROC of the original signal, say x of n. Okay, so now moving on to the next one. So how do I derive it, right? So now let us recall the fundamentals again. Everywhere if you go, you need to be very clear about the fundamentals, that is x of minus n, sigma n equals minus infinity to plus infinity x of minus n z power minus n. Okay, so now this minus n I can substitute as L, substituting minus n equals L on the RHS. So this one is RHS. On the RHS we get okay, so z transform of x of minus n, that is, so sigma n equals minus infinity to plus infinity x of L, so minus n, it is L, so z power L. Okay, so what I can do here is I can have L, z power L being written like this also. N is equal to minus infinity to plus infinity, that is x of L z power minus 1 whole power minus L. Okay, so this function here, which is z power minus 1, I can write it as x. Yeah, so I think I have to replace the summation here also as a new variable. Yes, so L would be from minus infinity to plus infinity. It would be minus infinity to plus infinity here. If I can replace it as L, exactly, yes. So now this function here can be represented as x of 1 divided by z. So this is z power minus 1 which is there. If you recall the function, so this is z power 1 multiplied with minus 1, minus n there. So this one here, which is z power minus 1 multiplied with minus L. So if it is z here, that would lead to x of z. So now this is z power minus 1 which leads to x power, x of 1 by z. Okay, so that is how you can arrive at the time reversal sequence of a given signal, say x of n. Okay, I hope you have understood all the properties which are related to the z transforms. I can move on to the next topic, which is transform of useful sequences. The transform of useful sequences. When I say useful sequence, it is a signal which is generally taken, and I can write down the heading as transform of useful sequences. Of useful sequences. Transform of useful sequences. First one, that is delta of n. So second one, that is delta of n minus n naught. Third one, that is delta of n plus n naught. So what happens if I take the z transform of delta of n? So this one, that is z transform of delta of n minus n naught. This one, that is the transform of delta of n plus n naught. Okay, so how I can write this? What is the z transform of the given signal? Let us go in detail. And before I go to the next few topics, I want you to remember the formula again. I'm stressing on it. So just to ensure that you don't forget the formula of the z transform, which is also expressed mathematically, I can say it as sorry, this is minus n. Yes, so it is z power minus n. Power minus n. Okay, so this is the formula. This is related to z transform of x of n. So sigma, okay, sigma n equals minus infinity to plus infinity x of n z power minus n. Okay, so that's how I can write the given signal. Say z transform of x of n sigma n equals minus infinity to plus infinity x of n z power minus n. So let us go for the first signal, that is delta of n. So what do I call delta of n? Which signal it is? It is nothing but the delta function or Dirac delta function, which is there. Okay, so now, so what happens? This is the given signal, say x of n. So sigma will be n equals minus infinity to plus infinity delta of n z power minus n. So this delta of n will be equal to 1 only at n equals 0. So that is z power minus n, whereas n equals 0 there. So x of z, okay, so z transform of delta of n, that would be equal to x of z, that would be equal to x of z. So that is z power minus n. So z power minus 0, which is there, I can write it as z power 0, which is equal to 1. So therefore z transform of delta of, what you can remember, so the z transform of a delta function, the z transform of delta function or Dirac delta function is unity. So delta of n will be equal to 1. As I already told you, delta of n equals 1 at n is equal to 0 alone. So it is 0 when n not equal to 0. It is n not equal to 0. It is 0 when n not equal to 0. Okay, that is one thing that you will be analyzing there. So this is the unity, which is z transform of a delta function is said to be unity. Now go for the second one, which is delta of n minus n naught. Okay, z transform of delta n minus n naught. Okay, so now what you can do here is this one. I know the z transform. Let me derive it quite easily. So z transform of delta of n minus n naught. Okay, so it is quite clear. Okay, so it is quite clear. Let us understand the delta of n minus n naught. That would be equal to 1 when n minus n naught equals 0. That is n is equal to n naught, and 0 when n minus n naught not equal to 0. So n when not equal to n naught, it is equal to 0 mathematically. Okay, so this is how I can write it. I can write it as delta of n minus n naught equals 1, which is n minus n naught. Only when it is n equals n naught, it is equal to 1, and it is 0 when n is not equal to n naught. So this function, that is delta of n minus n naught, says sigma, that would be equal to n is equal to minus infinity to plus infinity delta of n minus n naught times z power minus n. I can write it as z power minus n at n equals n naught. So that would be z power minus n naught. So z transform of delta n minus n naught, that would be equal to z power minus n naught. Okay, so that is how I can recall the delta of n minus n naught, which is nothing but a delayed by n naught units, delayed by n naught units of a delta function, of a delta function, of a delta function, delayed by n naught units of a delta function. So the z transform of a delayed delta function, okay, that is by delayed by n naught units, I can write it as z power minus n naught. Similarly, z transform of delta of n plus n naught. So what it would be, z transform of n plus n naught. So I can have z power n naught, z power n naught. Okay, so this is how I can write the z transform of delta n plus n naught, that would be equal to z power n naught. So where n naught is another unit, say 2, 3 or something like that. So it is an advanced signal. Okay, so by n naught units, advanced by n naught units of a delta function, of a delta function. Okay, so I have derived it for 3 different cases, that is delayed by n naught units of a delta function, that is advanced by n naught units of a delta function, okay, and without any delay or advance. So you can have only the delta function delta of n being present there. Okay, so now what you can do is you can make an attempt to solve for the next one, which is nothing but the sinusoidal sequence, or else I will discuss it in the next class. So we will discuss about the sinusoidal sequence, say x of n. Okay, so when I say it is a sinusoidal sequence, I have sine of omega naught n times u of n, omega naught n into u of n. Okay, so the third one, which is ramp sequence, which is n into u of n, x of n being n into u of n. So we will discuss these 2 signals in detail, that is the sinusoidal sequence, okay, and also the ramp sequence, that is x of n, that is equal to n into u of n. Okay, so these are the sequence. As I already told you, u of n is there, so it would be a right-handed sequence, u of n, which is a unit step signal, okay. So this one is also presented as unit step signal, okay. So now what I can do here, I can just give you a hint where x of n, it is when it is used as a summation, n is equal to minus infinity to plus infinity, where sine of omega naught n into u of n is being present there, right? So u of n z power minus n. So sigma would be n equals 0 to infinity sine of omega naught n into z power minus n. So you can express in terms of e power, okay? So you have the exponential representation of a sine function, and you can write it like this. So I can give you a hint where the z transform of x of n, okay, where x of n is a sinusoidal sequence, okay. And the similar way you can do it for the ramp sequence also, and you can just conclude what would be the z transform of the sinusoidal sequence, okay, and make an attempt to solve for x of n is equal to cos omega naught n u of n. So make an attempt to solve for cos omega naught n into u of n. So both are sinusoidal in nature, because just taking sine would not be a sinusoidal sequence. We generally use sine as a function, but cosine function, which is also there, which is the co-angle of it, cosine angle of it, it is nothing but considered to be the sinusoidal sequence there. So next one would be the ramp sequence, which you can take, and you can conclude what can be done. Okay, so we will stop here meanwhile, and in the next class, if it is possible, I'll be discussing about the sinusoidal sequence and also the ramp sequence in detail, how to obtain the Z transform of it, and we will be solving few simple numerical problems where the properties of Z transforms will be used exclusively. Okay, so let me stop here, and we will end the class. Okay, thank you everyone.